Okay, well, let's get on to the subject of microfacets. Um, hmm, yeah, there's little tiny bumps that are microscopic. We call them microfacets.
Maybe sharing the screen might be good.
You know, that would be good. The good thing is the recording
I
does
was like
have.
looking for it. I like assume everybody else had like the graphics codex thing, and I was like, oh shit.
I'm sorry, guys. Okay. Good thing I wasn't like, doing anything significant. I was just reading. Um, but yeah, if you've ever heard of microfacets, this is just a description of microfacets without any technical jargon. Not jargon, but technical preciseness. I mean, there are surfaces, and they are smaller than what we can see with our naked eye, and they reflect light, non-mirror like. We call it diffuse. How much is it varies. And then their very basic Blinfong just has a single value for glossy reflection, where it's either uh, infinitely reflective or nearly matte. Uh, hmm.
The all specular light is when it's purely a mirrored hit from a microfacet.
Or there are the microfacets are the actual divots and hills and valleys are almost completely all in line with the macro surface detail. Um, hmm.
So I mentioned frosted glass, and um, I don't know if you have a technical explanation for this, but one time I was cleaning a some a light fixture that was frosted, and when it got wet, it became more clear. Like the light going through it was less diffuse, and
Huh.
I just thought that was weird.
So yeah, for transmission surfaces, the like diffusion that you get is well, at least it's based on roughness, the microfacet roughness, and IOR. So maybe the water change, I guess, changed the index of refraction, and the lower the IOR, the less responsive it is to the roughness. I guess in principle, although it's you're kind of talking, I think, about two different volumes technically, but
Yeah,
yeah,
I just thought it was weird.
that's the
Sometimes,
closest I could get to an explanation.
yeah, yeah, I haven't considered the index of refraction.
So I'm looking at a chart of IORs, and it says glass is like a 1.5, and water has 1.325, whereas air is 0. And so maybe it was clear because there was a step change from 1 to 1.3 and then 1.3 to 1.5. And so the index the refraction angle was, well, there was more angles in which light would refract and not distort heavily, if that makes sense. I'm guessing as to what the cause is, though.
I also might be misremembering how it actually looked. I think maybe it was just that the surface looked smoother, and that would just be due to the water on it.
Yeah.
I don't know.
It's if you want to get real deep into lens making and mirror making for like telescopes, you get very comfortable with the atomic scale of silicon and glass because you are trying to get, well, a perfectly mirror surface which has no microfacets. Therefore, you must work. You must try to make your work at that level. What am I saying? So
Yeah.
I hadn't thought about how you'd make. Where is it? Where did it say that? Glossy glass. Uh, Frosted glass. Yeah, it makes sense that sandblasting would do that because your sand has, well, a similar roughness, and so it's just taking, it's pitting the glass surface with little holes in it. Little, you're removing the uh, atoms.
Yeah,
Making
you're
a
making it
non-
rough.
Yep. Yep. So I'm not sure what this is referring to. We have our incoming and our outgoing vectors, the surface normal, and then we have a microfacet surface normal, which is not a which is not the normal of the surface. It's the normal of the little planes here. The half vector.
They mentioned the half vector is halfway between the incoming and outgoing angle.
Yeah, and it's kind of like it assumes that if your outgoing vector is in a certain direction, the surface it would have bounced off of has the half vector as its normal.
Yeah, so I think it's the amount of specular is the, I guess, like percentage of microfacets that had their normal be the half vector.
Yeah. The Blin Fong model's coming back to me where the half vector is used for the specularity. And so I guess yeah, this would imply that using the Blin Fong model, your specular reflection comes from a facet that's normal to the half vector. Yeah, I wish there was a picture of the cosine specular lobe here. Fong specular lobe. Just because I like the visual. Well, that's actually pretty spot on. It's a scratch
see
pixel
you screen.
picture. What?
You can only see the.
I know. I was, just.
Oh, okay, cool.
I was like, I was gonna quickly look for one. If I couldn't quickly find one, I'll just give up. But it's just like your specular reflection in the Blin Fong model is this lobe shape, and the more specular it is, the more elongated and thin it becomes, and it becomes more, uh, well, long and thin as you increase this specular exponent, and as you decrease it, it goes to 1 and doesn't have any specific directions going in, whereas the diffuse goes in all directions relatively equally. And so the Blin Fong model has this, two lobe aspect to it. Mm, yeah, that's the Blin Fong model looked good enough for now for computational hardware of the 1975 era. Okay. So this didn't get too deep into like modeling microfacets. It just kind of described a high-level description of them and how the Blinfong model might approximate it. Subsurface scattering, though, that's more interesting. Yep. Yep. Have you ever taken a light, like a flashlight, and put it like on the web of between your thumb and index finger? You can see the light through it because light will travel through some things quite far and come out at a place very far away from where it entered. So it will transmit into the material. Yeah, transmissive. Of course, the light can travel very far, whereas with skin, it doesn't travel that far. Well, that's just fun. Okay. I had to read this paragraph a second time to grok it. It's saying, subsurface scattering is a component of the total energy hitting the surface. You have to consider that the light that scatters, either specular impulses or glossy diffuse stuff, cannot transmit, so you have to calculate the amount of transmitted light as a separate value, as a sub-value of the total, so you're not creating light where it didn't happen before. Lambertian diffuse term. Perfectly diffuse. The outgoing radiance is distributed equally in all directions. So a perfectly diffuse surface has a radiance that is pretty much any direction, it's the total incoming radiance divided by pi. Oh no, the reflectivity.
It's basically the albedo, right? 'Cause if you have a different 3 channels for the colors.
No. I'm not. When I think of albedo, I think of like the. Oh, I guess yeah. Never mind. I don't know what I think of them. What I'm confused by. What?
Like each color channel has a different reflectivity, I guess.
Yeah.
Which gives color.
What What I'm confused by with this is okay, so it's saying that the Lambertian is constant, meaning this reflectivity, which is just between 0 and 1, is further divided by pi, but the reflectivity value is going to be constant regardless of the directions involved. Okay. See, I thought this was like a function where you take stuff in and you pass stuff out, but no, it's a constant, this whole thing. So this is just describing how, given a incoming and outgoing direction, the value is going to be this. Given any incoming and outgoing direction. Yeah, and so... So yeah, there's... The radiance is equally put in every direction, but that doesn't mean the photons go in... The same number of photons go in every direction. Is this just another application of the Lambert law? Or
I think it's just like describing why you still need it here.
Okay. So is this saying that the moon has a constant brightness across the surface except where it gets shadowed by, well, the self-shadowing from being at an angle between the Earth and the Sun?
I think it's saying that the cosine law does not apply for the moon.
Yeah.
Because, like, yeah, like even in a Lambertian sphere, you still see it get darker around the edges because of the cosine law.
Yeah.
But that doesn't happen with the moon.
It's saying that there is a term that cancels out the Lambert law term. So that's interesting. So it's L times F times the dot of I normal. So it has to, divides out. Interesting. Yeah, I never considered the moon's surface to be constant across the surface, but it does look pretty constant. I mean, there are, shadows where the craters are, and the regolith that has different absorptive properties. But, oh boy. Fresnel effect. Not the Fresnel effect, as I thought for a long time. Ah, so instead of getting the actual equations for Fresnel, which differ based on conductors, whether it's a conductor or an insulator, and the Fresnel effect is where the at strong glancing angles, the reflectivity increases, depending on whether it's a glossy specular surface.
Yeah. Another good example that I see a lot is if you're looking at the surface of a lake, right? If your feet are in the water, you look straight down, you can see,
Yeah.
straight down into the water, and you look across, you quickly see all you see is the surface reflection. So that's kind of it's all view angle dependent.
Yeah. Yeah, that's actually a real good example that we might think of as a different phenomena because it's water, it's not a table, but it's effectively the same phenomena.
Mm.
Just the light going into the table gets absorbed by the table rather than going down into the mud below. And then we have this famous approximation by Schlick, which has given me nan bugs once upon a time. But other than that, it's a really good approximation. Where you take the F. Does it explain what the things are? FO is the measured or estimated Fresnel reflectance at normal incidence.
So looking straight down or straight at the surface.
Yeah, so it's F0 because the Fresnel reflectance at 0 degrees, or perpendicular to the normal,
Yeah.
or parallel to the normal.
Yeah, at a grazing angle. Yeah, where's... What's the difference between these two? Oh, IO and I and O, okay. And it's a curve, so we have our transmission, which is 1 minus f of s, and so that's where this, I believe that's where this 1 minus comes from. Maybe. I kind of wish there was like I guess this should be a link to the thing. Oh, let's... Okay, I didn't see, where is it? Is there not a link? Is this not... is this a broken link? That's sad. Okay. Oh. I'm not gonna... Okay. But yeah. Partial coverage. Moving on. Okay. So it seems to be partial coverage describes combining media together into a single homogeneous surface such that when viewed at a distance it has the same effect as if you had viewed it up close and then zoomed out really far. When I say viewed up close, viewed as separate media and then, looked at it from really far away. So an approximation, because at the distances involved, the details become, all that high-level detail is turned into average detail. I've not thought about, averaging a bunch of columns and the air between them as a single medium. Like, not obviously, I have not specifically thought of that situation, but not even like I've not really considered the need to do that as a parallel for very small surfaces like cloth, where yes, it's a bunch of threads with some air between it, but viewed from a couple of feet away, you can't tell that there's air between the threads, and it just looks all the same. Let B be the radiance along array before turning F be the radiance reflected from the surface. A be the partial coverage of the surface. So A is a percentage of the surface covered by a material, where 1 minus A is the amount of surface not covered by the material, aka air. And this looks exactly like a linear interpolation formula, which is what it says it is.
Weird to have a different name for it.
Well, seems to be, you're starting with B and you're going between A, F, and B at alpha, parameterized on alpha. Which is interesting. It's like assuming the surface becomes a spherical cow and just averaging over it. Oh. So, yeah, okay, you could totally use partial cutoff for leaves on trees, where you have one big triangle or quad, and you have a texture that is a picture of leaves, a 2D picture, and you have the alpha, at 1 on the leaf and 0 everywhere else. And I guess it'd be 1 on the branches too, but yeah.
I guess that also helps for you could do like LOD stuff with that by just blurring the texture.
Yeah.
When you're up close, have it to be the discrete ones and zeros, but then far away, just have like map of like 2 pixels, and they're all like 50%.
Yeah. See, my thought with rasterization, this doesn't work that well because the leaves need to blend together well. They're not opaque surfaces, they're transmissive. So you'll get the top level leaves have a lot of light hitting them, but the bottom level leaves will be a fractional amount of that light. And combining that all correctly sounds hard. But we're also what?
Yeah, the alpha is not indicating transmission here. I think what they're saying is that an alpha value of 40%, so you can still have an alpha value at the edge of those leaves to blend, right? But it doesn't mean that it's transparent. It means that on that fragment, 40% of the material is present and 60% is not present.
Okay. Well, that makes more sense. Still, my point stands. If you want to do trees justice, you have to consider that leaves are typically very thin and transmit a lot of light, as well as block a lot of light.
Well, you'd probably be sad to learn that a lot of games use alpha cutout
Oh,
geometry
I
for
absolutely know that
foliage.
most games do that because it's hella expensive. But
You could still do that here though, right? Because you could have the partial coverage say like have your leaf be a quad, but then everywhere it's not a leaf, have it be alpha zero. But then where it is alpha one, you can still do the have a transmissive
right,
BSDF for those parts.
I think what Abwood was saying is that that's a completely orthogonal concept to the
Yeah.
partial cutoff, and you can combine them together, but that's not what the partial cutoff is really doing for you.
So using the alpha cutouts, you don't have to give up transmission.
Yeah, but you can because it turns out blending is hard. Anyways, color. Oh boy, color in quotes. Yep, that is a spot on definitional description of how color is not useful in an absolute framework. The modern the common conception of color is not useful because it's not a simple, well, it's red, it's blue, it's not a simple three RGB values. It's a whole perceptive complex where there's a distribution. I mean, there's a lot of stuff. Yeah, surface biology. Yeah, I do like the philosophical quandary of you cannot tell a person, born without vision, what red or orange or brown is. It is just not possible because it's a purely experiential phenomena to describe red or green or whatever color you want. And so, in the same way, a completely deaf person just doesn't know what sound is. I know there's varying degrees of deafness and blindness, so it's I'm speaking in absolutes for demonstration purposes only. Uh, um, yeah, actually, this gets to the above conversation about leaves, where the the red cloth and the red gel are very different phenomena. Where the scarf has a bunch of holes in it for air to go through, whereas the red gel transmits 50% of the light, or the low frequency light, but it covers the entire area. Oh, the shadow color is different. I didn't notice that until it was pointed out. Where the red gel casts a red shadow, whereas the red scarf doesn't cast a red shadow, it casts a, well, non-red shadow.
The other interesting thing is the surface reflectivity is present on
Yeah.
is possible on the red gel, but not on the scarf there.
Yeah, you can see you can see the white, well, white, light red strips where you can see the surface contours reflecting different parts of the table and whatnot. Whereas over here, it's just a uniformly uniform distribution of red and white pixels. Um, yeah, that's So I like how he introduced all these concepts, perceiving color, uh, partial surfaces, Fresnel effect, Lambertian reflection. Well, actually, I kind of already talked about that in previous chapters, but subsurface scattering and microfacets, and didn't go into very much detail on how to model them mathematically, which means that'll be done another time, because I don't want to start another chapter. I don't have any.
Can we see the table of content?
Sure. We have rendering algorithms. 1, 2, 3, 4, 5, 6. 6 chapters after this. But the rendering algorithms, transport graph, path notation, node types, operators, notable phenomena, direct and ambient illumination, coded ray tracing, path tracing, bidirectional path tracing, photon mapping, radiosity. That seems like a big chapter.
So the numerical calculus one.
Yeah. So is this a calculus refresher chapter? I feel like it is. Yes. And I'd be happy to skip it, and I'm just as happy to go through this chapter because I could use it with a calculus refresher.
Let's see. Well, it's have some numerical stuff, which I don't know
Yes.
how deep
Yeah.
it gets.
So we have. So this section seems to be getting into the stuff that we care about from a implementation standpoint, rather than just a theoretical foundation. I don't think I've ever heard of Las Vegas style algorithms.
Yeah, I never heard of this term. But also, I never know Monte Carlo is a city until much later.
I knew that just because I watched travel shows with my parents growing up. Like Sundays at 4 p.m. was travel show time. And the two presenters, one of them was exclusively European traveling, and another one was mostly European traveling, but occasionally would go to like other industrialized nations, but not that often. So Monte Carlo, because Monaco, I knew about that Monaco there. I don't know if I knew the exact name Monte Carlo though. Now that I think about it, regardless. Okay, I'm assuming we're not going to want to talk about. We're going to want to get off the graphics codex for this week and talk about other more interesting things like what all y'all have been working on, or doing, or interested, or reading.
Kind of continued my DirectX 12 stuff a bit, but there's nothing really worth showing that's different. But starting to clean up some of the code into like more concrete, like